Hello everyone. In this video, we're going to be talking about section 13.3, Statistical Inference. With this section, what we're really going to talk about is all of the stats that we, discussed in the last section in 13.1, 13.2, and reference to real life applications and really what we're looking at. So a population is a particular set of objects that we want to know about. All right, so this is the entire set that we are talking about. So for me as a high school teacher, I want to look at my juniors' ACT scores. So sometimes it is impossible for me to look at every single junior's ACT score because first of all, everybody in the entire, United States or the entire world, something like that, that's too many kids to take the data from. And it might be impossible, it might cost too much, or just wouldn't make sense spending that much time. So instead of looking at an entire population, I would look at a sample, which is a subset of the population. And with these different definitions, we are actually looking at defining some of the symbols. So before, when I told you guys that X bar was the mean, that's actually the mean of the sample. So the numbers we are actually specifically looking at is X bar. And before, I told you guys that the standard deviation was the lower sigma here. So it kind of gets a little bit mixed up and a little bit more defined in this section. So the mean of the population and the standard of the population are represented by these symbols. So mu, this is mu right here. That's the Greek symbol for the mean of the population. And then sigma represents the standard deviation of the population. Either way, you're setting up mean the exact same way. You're setting up standard deviation the exact same way that we set them up before. And then the mean of the sample is X bar. Of course, that's what we're actually calculating. We're not going to be able to calculate mu because we don't know everybody's ACT scores. And then the standard deviation of the sample, that's what was represented by S that I told you guys to represent by the sigma. Now, there are several different types of actual, samples here. One is a random sample. All right, random sample of size R is a subset of R individuals from a population chosen in a way that every subset has an equal chance of being chosen. So there are a couple different more types of samples, one of which is self-selected. I believe I did talk about this in class. And self-selected is when you are, replying to those emails, replying to those surveys, or you're choosing yourself, right? So you are selecting yourself to be a part of the data set. Another is a systematic sample. And that's where people are chosen systematically. So you can line everybody up in your class and do any, meeny, miny, mo, and every single mo that you are selecting is somebody that you're taking the data from. And one of the other types is going to be a convenient sample. Convenience. All right, and they're pretty much exactly what it sounds like. It's going to be convenient for me to collect. So a sample that is a convenient sample for me are the students that I have every single day in my classroom. It's easy for me to ask them a question. It's easy for me to get a response. In addition to those different categories, we have what are called biased and unbiased. So biased versus unbiased. If we have a biased sample, that means it over or underrepresents. And by over or underrepresenting, an example of a biased sample would be me surveying my dual credit calculus class on what their favorite subject is. Typically speaking, those students that are taking, those advanced courses, taking that calculus class, is probably going to be one of their, favorite subjects versus if I were to, just survey everybody in Algebra 1. It's a required class. It's not an elective. So if I were to survey what their favorite subject would be, I would get a larger variety of answers. If a sample is unbiased, it's going to more accurately represent the population. All right, if we're talking about this bias, it's going to underrepresent. You're missing out on a complete part of the population. Okay, so normal distribution. In various problems, you might see those words, normally distributed. It's normally distributed. So what this is really going to look like when we actually get to an example with actual data points is that right here in the middle, keep in mind we've been using x bar instead of mu here. All right, so x bar, that is my mean. It is right in the middle. So that average in my set of data is going to fall right there in the center. And then I'm going to have, an equal distribution of some numbers to the left and some numbers to the right. And we're going to see that when it comes to lots of studies and everything like that, the majority of the data is going to be really close in there with the mean. All right, and it does give you a percent here on this drawing. So this is within one standard deviation, so plus or minus one standard deviation. And I am going to go ahead and write that, plus or minus one standard deviation. And that is 68%. That is 68% of the data. 68% of the data is going to lie within one standard deviation. So that is 68% right there. And then if you were to expand it, 2 standard deviations. So that means from the mean, I am expanding 2 deviations to the right, 2 standard deviations to the left, and that's going to be 95% of your data. All right, so if it says that it's normally distributed, 95% is going to fall within 2 standard deviations. So if you were to expand it to 3 standard deviations, that's 99.7% of the population is going to lie within that amount. So they go ahead and throw in those big dotted lines right there. Now, this curve does expand all the way out to infinity. So we could have a ton of outliers. Well, not a ton of outliers. We could have some outliers on either end, and this normal distribution would include it, but it's going to be a really, really, really small percentage. So those outliers are out there, but 97% of our data is going to fall within 3 to the left and 3 to the right. So it is within 3 standard deviations. And these are, different percentages that are used pretty regularly. So right here is a rule. So it says the 68, 95, 99.7 rule. Okay, so with this lovely picture that you saw up above, I'm actually going to go ahead and draw a, ghost. It does look like a ghost. I'm going to draw a normal curve, and I'm going to go ahead and put x bar, my mean, right there in the middle. 1 standard deviation to the left and to the right. Then I'm going to draw in 2 to the right and to the left, and 3 as well. So if 68% is lying within 1 standard deviation, that means that this is 34% and 34%. And if it is then expanded to 2 standard deviations, and that's 95%, I can go ahead and subtract and then divide by 2, and I would get 13.5% is contained in that amount. 13.5% is contained between 1 and 2 standard deviations, and I can keep going and doing this. Now, if I'm talking about the total probability, all of the area underneath of this curve represents the probability. So 34% here, 13.5% here, and then it goes on to 2.35% and 0.15% all the way at the end of the tails. So if you were to look at the left tail, by the way, left tail, I'm talking about this area here, and the right tail, I'm talking about this area under the curve there. That is 0.3% altogether. So outliers are not going to be very common here. when I'm referencing a normal distribution. Now here's a little bit more of a cleaned up picture. There should be an arrow going from the second deviation all the way through, so that's 95%, 68, 95, 99.7. Okay, so what is this actually going to look like when I reference an example here? Let's check it out. So a manufacturer produces bags of navy beans and it says net weight. What does net weight mean? That is actually your average. All right. So that's kind of what they're averaging here, but it actually says that the mean itself is 8.2 ounces and it has a standard deviation of 0.09. So here's what we're going to do. We're going to go ahead and draw an approximating curve. All right. It says that it's normally distributed. I know this curve isn't perfect, but right here in the middle is 8.2. So when I'm doing that plus or minus standard deviation, what I'm genuinely doing is adding and subtracting that amount here. So I'm going to go ahead and do that. I'm going to do 8.29. I added that on. 8.38 here, 8.47. And then I'm going to go the other way by subtracting. Okay, so I have my entire curve filled out here, and it wants to know what is the probability? What is the probability? So we are looking for decimals instead of percents here. That the bag will be between 8.11 and 8.38 ounces. So here is 8.11 and here is 8.38. If I remember, this is 34% or 0.34. 0.34, and this is a 13.5. So well, not a 13.5. It's going to be 0.135. 0.135. All I need to do is add those together. So that is a 0.68 and a 0.135 added together. So that totals 0.815 or 81.5%, but it does say probability, so we're answering it as a decimal. And if you were to look at this on a normal curve, it would look like, 81% of the curve is kind of covered between those numbers. And for number 18 here, this was off of my Algebra 2 test, it says, what is the probability that it's going to be more than 8.47? So I'm just looking for this area. And if you recall, that's going to be 0.15% or 0.0015. So there are not going to be a lot of bags that have more than 8.47 ounces, which makes sense. If they're trying to regulate it, they don't want to be, giving anybody a ton of extra beans. Okay, right here with number 21, this is another way to ask this type of question. So 500 students took your school, or 500 students in your school took the SAT test. Assuming that a normal curve, so that's what we are looking at when we're looking at a normal distribution. It is a normal curve. How many of those students scored within 2 standard deviations? So if you recall, we had these 68, 95, 99.7. So 2 standard deviations is 95%. That is 95% of the students were within 2 standard deviations. So how many students actually scored within 2 standard deviations? Take 95%, 0.95, multiply that by 500, and you get 475 students. All right. We do have a couple of other questions here that ask about the margin of error. That formula is not presented in this section, but just in case you guys want it, the margin of error is plus or minus 1 over the square root of n. And n in this case is the population number. All right, it's a really small formula, but it's not tested. It won't be tested over. So z-score is another way to use a normal distribution or normal curve. However, if with the bean example, if you noticed, I used my mean here and then I used my standard deviation. Instead, if the number that I'm asking about doesn't lie exactly on one of those lines, what am I going to do? I'm going to use a z-score. So x is the actual value that I'm looking for. So with the bean example, I was looking exactly for, 8.11 to 8.47. All right, those fell exactly on those standard deviation lines added to the mean. Okay, if instead I were to ask about, I don't know, what about 8.15 instead? There's 8.15. It's not exactly on one of those lines. So x is the actual value I'm looking at. That's where the 8.15 would go. Then I subtract the mean, and then I take it over what I've been calling sigma, or what this textbook has labeled as an S. All right, and that is the standard deviation. So we get a z-score, and we are going to round this to 1 decimal place. So 1 decimal place. All right, so it might come out 0.7, might come out negative 1.2. Make sure that you are rounding properly, and then we use a chart. This is where I said if you're a statistician, you are using a whole bunch of charts, and you're using this data that is easily Googleable. Okay, so let's look at it. Find the z-score for a box weighing 19.4 ounces. So, in this example, it says that it has a mean of 20 ounces and a standard deviation of 0.25. So, what we're going to do is take that 19.4 minus 20, and then we're going to put it over the standard deviation, 0.25. So, we get negative 0.6 over 0.25. And we get negative 2.4 here. Get negative 2.4. So that is my z-score, or that's my z number here. So I'm going to use that negative 2.4, and I'm going to go down on this chart. So I have a negative 2, and then I'm going to go over to the 0.4s, negative 2.4, and that right there means 0.0082. 0.0082. So what is the probability? It's not even 1%. If I go ahead and round it, it's 1%, but it is not likely that it's going to be scoring under that 19.4 here, or scoring that 19.4. Because if I were to think about it, if the mean's 20 ounces and the standard deviation is 0.25, that means 1 standard deviation away, I'm at 19.75. 2 standard deviations, I'm at 19.5. 3 standard deviations away, I'm at 19.25. And I'm asking about 19.4. It's outside of 2 standard deviations, so the probability is not going to be very high. Okay, hopefully you guys found this informational. If you have any questions, please email me or come to class with questions.